quantization method for dissipative systems. I will have to speed up my presentation a little bit because I have to pick up my son in school, constraints of normal life, but I think it will be understandable. Thanks the organization for having me here. Let's begin. I will begin with some preliminaries about how this problem has been tackled along these years. The problem has begun almost since quantum mechanics has come to life in the hands of Heisenberg and Schrödinger, and it took two different strategies. The first one, the first that was tried, was a more direct approach that assumed open physical systems with phenomenological dissipation given by this kind of force. And another strategy was assumed appeared a little bit before, after, that took an isolated physical system and divided this system into subsystems. One of them with a lot of accessible states, which take energy from the other system. So when you look into one of the system, the one with little accessible states, you see energy being drained. So it's a clever way to, I believe, it's a clever way to look to a dissipative system inside an isolated one. Okay, you will find numerous references in the literature about these two problems. The first one, the blue one here in this column, has the problem that you have to reform, or at least to expand, Hamiltonian mechanics to make quantization, and it's very difficult to do. A lot of trials have been made during all these years, and some proposals have been presented. But one of the problems here is to make this extension. In the other side, you, in general, has to model a specific heat bath, the second system, which generally is done by using harmonic oscillators. The Caldera in Leggett is a obvious reference on this side. Well, we do neither of this. We keep Hamiltonian mechanics as it is, and still assume that we have to tackle the problem of non-Hamiltonian systems using that dissipative force. And you do that, as you'll see, by assuming an equation from which quantization is performed, and then change that equation, which is basically Liouville equation, but with some qualifications. And we reform this Liouville equation to introduce dissipation. And when make a quantization method which is axiomatic, you will see briefly, we get a Schrödinger equation that encompasses dissipation in a little bit different way than is commonly seen. Let's go to the axiomatic approach. I will begin with Hamiltonian systems. It's a strategy to improve your confidence in the quantization method so that you can at least believe in what I will say about non-Hamiltonian systems. And this axiomatic approach is quite easy. It is the definition. This is not an axiom, of course. It's just the definition of a characteristic function defined over fibers in the phase space, fibers in each position of the configuration space. This is not an axiom. It's done currently in statistical physics, in statistical mechanics, and in statistics, whatever. But now we assume that your characteristic function can be written this way. This seems quite similar to the approach of Wigner. We have seen previous presentation talking a little bit about that, but there is a difference here in the quantization method that you will develop this characteristic function only to second order in the parameter delta q. Delta x, I almost sometimes write x, sometimes write q, is the same thing. The other axiom, and the only other axiom here, is that the phase space joint probability density function fxpt obeys that integration, which is, of course, the Fourier transform of the Liouville equation. The Fourier transform over the momentum space, of course. If you have these two axioms obeyed, it's easy to show that you can mathematically derive the Schrödinger equation. I will do that first for Hamiltonian systems, and then I will show how to generalize that. So the derivation process is very easy, very simple. You have just to expand the Liouville equation. I have used, of course, Hamilton's equation somewhere there. You take the Fourier transform indicated in axiom 2, and you get an equation for the characteristic function in terms of x and delta x. And then you write the probability amplitude in this way, because it's a complex function, and use the first axiom to write the characteristic function like this, expand it to second order, you have this result, and substitute it in the previous equation in blue. When you do that, you get two equations. You get these two equations in zero order. In delta x, you have the continuity equation, which is here. And in first order in delta x, you have Bohm's equation, which is here. And we know that if we have psi given by that expression, and you substitute it in the Schrödinger equation, we get exactly these two equations. The first one real, if I'm not mistaken, and the second one multiplied by a complex, the complex I, imaginary. So you have exactly the same equations when we divide the equation into real and complex part. And so if we get these last two results, we can show, of course, that they are equivalent to the Schrödinger equation. This is the method, just that. You can use Maple, you can use whatever you want to perform this kind of quantization. Okay, but we should get a little bit confident about this quantization method, Hamiltonian quantization method. And it's nice to see what happens if I try to quantize in generalized coordinates. Of course, I'm not using the usual method of quantizing in Cartesian coordinates and then change to the spherical coordinates or generalized coordinates that I want. In an axiomatic approach, I can do that, but it must be true that if I write the axioms in the desired coordinate system, I will certainly get the Schrödinger equation in this system. This is an imposition of the on the quantization method. So we can do that. We then express the characteristic function in this way. We expand the Schrödinger equation. I'm assuming spherical coordinates. And I am assuming a Hamiltonian, usual Hamiltonian with potential depending on R, vector R. So you have the second axiom written by this without the integration, of course. And you repeat each step of the previous derivation, and you get exactly the same result. And the continuity equation written in spherical coordinates and Bohm's equation written in spherical coordinates. Then the method seems to function for any system of coordinates. This may seem a little bit trivial, but it's far from that. Although it is straightforward, it's not trivial anyway. I will show you why this is not trivial. I've said that this characteristic function, this is the Liouville equation, not integrated yet. This is the equation that you get for z function, the characteristic function, when you perform all those steps. The characteristic function expanded to second order is in terms of x, in terms of the Cartesian coordinates is given by that. You have just to change to your coordinate system that you choose. In this case, you have to change that derivatives over there to these ones show here. Here. Where is he? Here. And you have also to expand these elements in coordinates, in the spherical coordinate system. This expression for z becomes enormous. This is possible to do only, despite the fact that only very straightforward operations are in place. You must do that using a algebraic computation approach, or you won't get the results. I've tried for some days, and it's really impossible. If you see that happening in Maple, when you present these characteristic functions substituted, written in these terms, in spherical coordinates, and substitute it here, you get an expression that has in PDF 90 page approximately. So it's almost impossible to find the correct results doing that. But if you do that, you obtain exactly what I've said in the previous slide, which is the continuity equation for zeroth order in delta R, and the Schrödinger equation in the first order parameter. So, as I said, this is not trivial, although it's straightforward in the sense that only usual operations were performed. In fact, I was vindicated by this use of straightforward word in my paper, because every time you find straightforward calculations in the papers, we know what happens. So it was nice to be able to write it. Okay. It's possible to generalize the method using an electromagnetic extension. Of course, we have an Hamiltonian in this way. We have a characteristic function with the canonical momentum represented there. We have, of course, we perform, of course, the same steps, and we get exactly the same result. The continuity equation and the Schrödinger equation. Well, at this point, I believe we are confident enough of the quantization method. We can extend this to relativistic approach too, to find second order equations. only second order equations. And we can then try to understand how to generalize that to a non-Hamiltonian approach. See, I've used Liouville equation because I was using Hamiltonian approach. But of course, I can write that derivative without assuming Hamilton's equations. So the fact is that I don't depend on a Hamiltonian to make this kind of quantization. I can take the generalized Liouville equation, the Liouville equation generalized to encompass dissipative or absorptive systems. But I will talk only about dissipative systems. It's the same thing. And to do this generalization of the Liouville equation, we take the infinitesimal phase space volume element and we calculate the number of systems that are inside this volume, which is given by this expression. Of course, it's usual. And we calculate the number of systems entering, flowing to inside this volume, which is given by this, the velocity plus the area element, multiplied by the density, of course, and the number of systems out of this volume element, which is given by that expression, which is almost the same, but taken in the other surface. We then subtract one of the other, and we get this expression. We can divide by delta V, which is the volume element, and if we do that, we get this expression in F, and when we substitute in the above formula, in this formula over here, these elements here are the expression when put this side of the Liouville equation, but without assuming that x dot is expressed in terms of a Hamiltonian, but expressed in terms of Newton's equation, of course. It's possible to do that. And we end up with this generalized Liouville equation. This last term is generally called a compression factor, which is the divergence. The process of derivation shows that it's a divergence on the surface x and the surface of P. For Hamiltonian systems, this term is 0, and we get again the usual Liouville equation. Okay, this is the generalization of the equation. Then I will try to apply the method on this equation. That's why I've said that I was not trying to generalize the Hamiltonian approach. I will make a workaround. I will use Newton's equations in this kind of approach and make the same steps, same quantization steps I have already presented. Can we do everything as before? Yes, we can assume this phenomenological situation. I'm calling phenomenological because this is a phenomenological parameter. Then we do everything as before, and we get this equation. The continuity equation with some term and this equation, which is, if we compare with the previous result, the Schrödinger equation, but with this term here. This term is a problem because to get S, we have to do some mathematical approach. But what is nice to see is that doing the quantization, we get in terms of Bohm's symbols exactly the same equation that was expected. These I put the gradient here, of course, and when I do that, this is gradient of S is P. So I get this. This is Bohm's Hamiltonian. This function can be can be a function of x, and then it has to appear. This is the Hamiltonian, and this term is this is the Bond's potential, né? Quantum potential, and this is the gradient of S is just P, so those two equations are pretty much equivalent. But the fact that is that to express these in terms of the wave function, because I want the equation in terms of the wave function, I will have to include this nonlinear term here. This is not a very nice representation of the problem, because this will lead to a nonlinear equation that will be difficult to solve, almost impossible to solve analytically. So it's an inconvenience, in fact, more than an inconvenience, for reasons that I won't go into here deep. We, of course, expect the shrinking. I will try then another approach. We expect shrinking of delta V, for dissipation at least, and we will change the kernel, the Fourier kernel, here in these terms. Why is the rationale of this? You must make the derivation to see that. But when you make the derivation, there appears a term in the characteristic function that is exactly that term that gives the momentum dependence in the end. And when you inspect this equation, you see that if you introduce this term, it's possible to remove this term, dependent term of the equation. So if you do that, which corresponds to an exponential decay of the phase space volume because of dissipation, you perform the same steps before, you get this Liouville equation, this equation for the characteristic function, without that term, which gives the dependence that I was trying to remove. And if you expand this new characteristic function, I expressed it by zeta to make it different from the z I was using before because of the difference in the Fourier transform. You get this equation. This is an equation which seems to be, if you look here, as if I've changed the Planck's constant by that expression. This is the same that you get here, and it's the same that you get here. If I write instead of h bar, I write h bar times E minus gamma T over M, I have this equation. Well, of course, this equation is not easy to solve, but it can be solved for some trivial problems, infinite potential, square potential. But the most interesting for us here is to solve it for the not minimum, Gaussian wave packet, to show how the Gaussian wave packet, of course, submitted to dissipation, will develop in terms of time. So to do that, we find the free particle. It's not free because it's submitted to dissipation, but free in the sense that there is no potential V. I put gamma as m omega to remove some irrelevant constants, and you find the probability amplitude solving the equation that equation that I've shown in these terms. you insert a structure factor, a Gaussian structure factor, to have a Gaussian wave packet, and make the calculations to get this probability density function. And this probability density function is very easy to simulate, and you can see what happens to the Gaussian wave packet, choosing some values for the constant there. Of course, h bar, m, omega, k0, I put everything equal to 1. I think I put b equal to 6, if I'm not mistaken. And you get this result here that I will show you as a little movie, which was done in Maple. Look what happens. The Gaussian wave packet begins to move in the way expected, but instead of getting its standard displacement bigger, it gets it smaller. There is a localization of the state, and this is very easy to understand. The systems with that are on my right in the wave packets have greater momenta. Then they are affected more than those systems here. So I have this, when moving, I have this kind of quenching here. It's moving, but it's moving slower here than here, and then I get the quenching of the system. Okay, so this is what we expect, because in terms of Newtonian mechanics, what you have when you have a force, a dissipative force of that kind, you have the system going to, when you don't have a potential, you have a free particle, you have the system going to momentum zero. Okay. Well, this is, of course, the situation for free particle with dissipation, or an open system of free particles. And you may now ask about what happens when you try to solve the generalized Schrödinger equation for any v which can be of some physical interest. Well, I don't have this. Let me put here. I don't have the answer, because it's very difficult to solve that equation, but I invite someone interested in trying this to contact me for maybe try to solve that. But in the general case, what we have is that P is the generator of translation, and while Vx, assuming a Vx of a force that increases momentum, x minus omega t decreases it. So we may find at some instant, we may find an equilibrium, or we may find the complete dissipation of the energy. I don't know what may happen in this case. Only the solution of the equation will, of course, give the answer. In any case, it's nice to understand that if this approach makes any sense, it probably can use to study trapping of ions, trap of atoms, trapping of nanoparticles, etc. Okay, conclusions. We begin with a reliable method of quantization. We based our approach on an equation which bypasses Hamiltonian approaches. It's not It does not need uh, the the Hamiltonian formalism, and we then find a generalized Schrödinger equation in which movement, at least for the system under scrutiny, shows stops after some time reproducing the Newtonian case. Well, this is what I want to show you. Thank you very much.